This is lecture 15, properties of functions. Well, we've already seen some properties of functions, but we're going to look a bit more carefully at them today. I'll start by reminding you something about graphs of functions. So start with, this time, we had sets A and B before. This time we've got sets x and y, which is perfectly reasonable. And f is now a function from x to y, rather than from A to B. It doesn't really matter. Okay, so in this case, the graph of the function is going to be a subset as a Cartesian product, x cross y. So remember, x cross y, oh, that's a strange colour. I'll just try a different colour. X cross y, you'll remember it's a set of all pairs x, y, such that x is in x and y is in y. And now if you've got a function from x to y, then the graph of the function picks out those pairs which belong to the graph of the function. In other words, it's those where the second coordinate is equal to the function value at the first function evaluated at the first coordinate. So we also said this was also equal to xy in the Cartesian product such that y is equal to f of x. And the following statement, I'll remind you again, is always true for any function from x to y. It's not a special property of the function. No matter what many people have written in previous exam papers about this, this is not a special property of functions from x to y. This is something that all functions from x to y do. For every x, there's always a unique point y such that x, y is in the graph. You could write that in math symbols as, for all x in x, there exists a unique y in y such that y equals f of x. That tells you something about not getting repeats of the second coordinate. Not getting repeats of the first coordinate is what I'm trying to say. If you repeat the first coordinate, you've got to repeat the second coordinate with it, which means it's only really one point in the graph. You will see on question sheet 3 some examples where the first coordinate appears to get repeated, but the second coordinate happens to be the same again. So it's really only one point in the graph. Because sets don't care how many times you mention each of their members, it still only counts as being an element once. So that's why I say there's never any repeats of the first coordinate among distinct ordered pairs in the graph, but if you happen to find the same ordered pair in the graph for two different reasons, that's okay. As long as it's exactly the same ordered pair, that's fine. And that's the only sense in which you could get a repeat of the first coordinate if it actually had the same second coordinate as well, and was therefore really only one point, the same point in the graph. Right, but depending on your function, you may or may not get repeats of the second coordinates, the function values. So it may be, depending on the function, that if you change your x value, you might still happen to get the same y value. So we're going to start by talking about injections or injective functions. These are the ones where you don't get repeats of the second coordinate. So this is something special about the function if it happens. And we're going to look at these two contrasting functions, which have got standard graphs, which you can probably draw better than me, especially since I'm using a tablet. So I'm going to draw two different curves. So I start with y equals x squared, which was supposed to go to the origin, so I'll just try that again. And it's symmetrical. So you can try and make it look more symmetrical than I did. That's y equals x squared, and then y equals e to the x goes through at height 1. And has an asymptote at the axis. Okay, so this is y equals e to the x. And now it asks about horizontal lines and how often do they cross these graphs, which is the key to figuring out what sort of properties your functions have got. So if I go across somewhere up here, this line crosses the graph twice, or intersects the graph twice. Down here, your horizontal line doesn't intersect at all. And the axis intersects the curve exactly once. That's the x-axis. Okay? So we've got some meeting it no time, some meeting the curve once, and some lines meeting the curve twice. But e to the x is slightly different because wherever you look, the line either meets it no times or one time. So, for example, here, again, we've got no intersections. But no matter where you try up here, once it does meet it meets it exactly once. So there's a difference between these two functions because although both of them have got some lines which meet the curve no times, and both of them have got some horizontal lines that meet the curve once, x squared has also got some horizontal lines that meet the curve twice. Okay? And that's something that e to the x doesn't do. So that tells you there's some difference between them. And this one, the difference between them is that one of these functions is injective and the other one isn't. So the e to the x curve, you don't get any repeated y coordinates. Now, neither of them get repeated x coordinates, right? Vertical lines still, either of these curves, the vertical lines still meet them once, because that's true for all functions. Okay, so there's nothing special about the vertical lines. There's nothing special about the fact that you only get one value for each x. There's only one y. Okay, but what's different between them is whether for each y there's only one x, and for x squared there are y values with two x's. Of course, both of them have got y values with no x's, but that's not important here. What's important is whether you have any y values that get more than one x, and x squared has that. Okay, so what is an injective function, or an injection? If in the exam you get asked to say what an injection is, I suggest you use some definition like this one, rather than trying to make up your own one. You've got sets x and y. You've got a function from x to y. That sets the scene. What does it mean to say that f is injective? It means that whenever you've got two different x values, call them x and x prime, they must be sent to different y values, f of x and f of x prime. So if x is not equal to x prime, we must have f of x not equal to f of x prime. And that fits with the e to the x curve satisfies that, whereas x squared doesn't. So e to the x is the example of an injective function here. In terms of the graph of the function then, your function is injective, if and only if there's no repeated second coordinates among, and that word distinct ordered pairs, of course. Each ordered pair in the graph only counts once, really, but you, as I've said, especially on question sheet 3, it can look a bit confusing because there could be several ways of getting at each of the ordered pairs in the graph. But they only count once each, really. So a function is injective. If you've got two different ordered pairs in the graph, they mustn't have the same second coordinate. Another way of saying that, for every point y, there's at most one x with f of x equals y, because there don't have to be any at all. You're not required to be able to get at everything. You may or may not be able to get at everything in y, but as long as you can't get at anything in y twice, then you're okay. And you can do it in terms of pre-images. The pre-image of the single point set y, that we defined pre-image last time, that's the set of x's which get sent into that set. But since there's only one thing in this set, it's those x's, so that f of x equals y. Okay? And that's a pre-image of the single point set y. And it must never have more than one element. Okay? So you can detect whether you're injective. This is an equivalent standard definition you could use if you want. Each of these pre-images should have at most one thing in. So for every y, there's at most one x. We already know for every function that for every x, there's exactly one y. So that's completely different. That's something that's true for all functions, not to be confused with this, which says that for each y, there's at most one x. Okay, so you can look at the graph of a function, and even if you don't know what the codomain is, you could still figure out from the graph whether it's injective. These y equals e to the x, y equals x squared graphs, whether they're injective or not, it doesn't change whether I was regarding them as a function taking real values with codomain R, or whether I was taking the codomain to be the positive real numbers, non-negative real numbers. Couldn't have been the positive real numbers for x squared. Could have been for e to the x. For e to the x, I might have had my codomain being the positive real numbers. It wouldn't have affected the fact that they were injective or not injective. So we're going to have a look at some sets of ordered pairs, and I'm going to ask you to try and figure out which ones are the graphs of injective functions. I noticed I'm missing a word here. That should say, note that to be the graph of an injection. To be the graph of an injection, it's got to be the graph of a function in the first place, and it has to be an injective function. So there's two different things to check. First of all, it's got to be the graph of a function, which you know is something to do with the first coordinate, and then it's got to be an injective function, which you know has got something to do with the second coordinates. Well, again, it's some in the way they interplay. Okay, so here's the question then. How many of these three sets of functions, three sets of ordered pairs, are graphs of injective functions, injections? In other words, first of all, are they graphs of functions? Otherwise, you can rule it out. And then if it is the graph of a function, is it the graph of an injective function? So I'll give you a few minutes to think about that. We'll see if you've understood the question as well. But you can vote any time because I've zeroed the votes. So let's see what people went for. Last chance to vote if you haven't voted yet. ...49 responses with A majority in favour of B, with a reasonable number going for C. Okay, B is the correct answer. Let's see where the problems are. Okay, the second one is not a function. The second one is not a function at all because of the repeats in the first coordinate. What is f of 2? Okay, so this is not a function because f of 2 is both 1 and 7. We're not allowed to do that. So the graph of function can't have a repeated first coordinate with different second coordinates. Okay, so that's not a function. That rules that one out. The other two are functions. The other two are functions. So S1 and S3 are graphs of functions. S1, though, has got a repeat in the second coordinates, 3 and 3. So this one's got problems because f of 1 equals f of 5 equals 3. So this one's not injective. Now the last one, you may recognize that you square the first coordinate to get the second, and you could conceivably think that squaring is not injective because we saw a moment ago that squaring is not injective. However, just because squaring isn't injective on the whole real line, it can become injective if you use just a few real numbers like these ones, because here there's no repeats in the second coordinate, so this is an injective function. And the fact that it comes from squaring doesn't actually matter for that calculation. The main thing is that if this is the whole graph of the function, then in this graph we haven't got any repeated second coordinates. We also didn't have repeated first coordinates because we needed that to make it a function in the first place. Okay, so any questions about those examples? One of the things you see, though, if you do spot that that's x squared, then that shows that you've got to be careful with x squared. You have to keep track of which your domain is. And here, squaring is not injective if your domain has too many points in it, like the whole real line. But squaring could be injective if your domain is, well, one where you don't get repeated squares. Okay. So now the other side of the coin, now we've looked at injections, we're going to look at surjections. Now, we've already done x squared, and so I don't think I need to repeat x squared again, so I'll do x cubed minus x. Well, for x squared, I'll just go back and remind you that some of the lines met it. Some of the lines didn't meet it at all. Some met it once, some met it twice for x squared. X cubed minus x is a nice graph, though. Quite a useful graph, that one. So here's my attempt at y equals x cubed minus x. That one very good. Try it again. Should have gradient minus 1 when it hits the origin. If it hits the origin. Last try. You can put more details in here. We know what these three places where it crosses the axis are. You have to do a bit more work to find out where the stationary points are, but you can do that by a bit of easy calculus and find out the heights and so on. It's an odd function, so you have to rotate it around the origin to get from the right side to the left side. And when you look at various horizontal lines here, they all hit the curve at least once. Here we hit it once, here we hit it once, here we hit it 3 times. You can find some places where it hits twice and so on. You can just manage twice. So you can have one intersection here, 2 intersections here, 3 intersections, and back down to 1 intersection here. But what you can't do is get no intersections with x cubed minus x. Whereas with x squared, so see earlier for x squared, some horizontal lines had no intersections. Remember, it's the horizontal lines that matter. The vertical lines are very boring because the vertical lines always hit the curve exactly once, whatever function you deal with, as long as you stay in the domain. So the vertical lines are never interesting, but the horizontal lines are. So the fact that every line hits this curve x cubed minus x at least once tells you that every y value, for every y value, there's at least one x value. Whereas injective, we were looking at for every y value, there's at most one x value that can get you there. If you're surjective, for every y value, there's at least one x value that can get you there. So surjective is also known as onto, and if you want to remember which is injective and which is surjective, sur is French for on or above, or variants of that. But if you want to think of it as on, that'll be an easy way to remember that surjective is the one that maps you onto the whole of the domain. I'm afraid into doesn't mean injective, so don't use into. Into just means that's where your codomain is. So into doesn't tell you you're injective, unfortunately. There is another term for injective, which I haven't put in the notes this time because it always causes confusion, which is the term one-to-one. But one-to-one, you don't know which is the one, and everybody gets it the wrong way round. However, 2-to-2 is quite good. So if you want to think of injective as being a 2-to-2 function, so if you take 2 different x values, they go to 2 different y values. But taking 1 different x value means you go to 1 y value, doesn't tell you anything. So 2-to-2 is better if you want to think about injective. But you'll find 1-to-1 in the literature. I'm just avoiding it to try and avoid the confusion. Right. So we had injective, now we've got surjective. A surjection is a surjective function, and it's just a function where you get to all the values in the codomain. Now, this is slightly problematic because you can have the same domain and the same rule, but you can change the codomain. And if you make the codomain as small as possible for the function to make sense, then you always end up surjective. Whereas if you take a bigger than necessary codomain, then you're never surjective. So if you're trying to figure out whether you get to every value in y, you need to know what y is. And so you have to know what your codomain is. And that's one reason why in this module, when we're trying to figure out if things are surjective or not, you really need to pay attention to what your codomain is. So, for example, if you have the rule x goes to x squared, then it doesn't give you a surjection from R to R because of all those horizontal lines that missed the curve. All the negative real values that you can't get at. So you don't get a surjection from R to R. But if you use the same rule as a map from R to the non-negative real numbers, then you can get at every non-negative real number as a square, and so the function is suddenly surjective now. So with the same domain and the same rule, depending on which of these you take to be a codomain, it's either surjective or it isn't. And that's a problem when you're dealing with functions in this level of formality. If someone tells you if someone gives you the function and says, is it surjective, they have to tell you the codomain or you can't answer the question. They better tell you the domain as well. So I won't spend more time on that because I want to move on to functions that are both injective and surjective. But I suggest, if you do want to think about this, draw sketches of random functions you've heard of, or look at all the sketches that you've been given in calculus, and have a think about which of those functions are injective and which ones are surjective, and which ones are neither, and which ones are both. Now, if you're injective and surjective, then you get something that's bijective. Now, if you remember, injective meant that every y value came from at most one x value. And surjective meant that every y value came from at least one x value. So if you're injective and surjective, then every y value comes from exactly one x value. Right? So for all y and y, there's exactly one point x in x with f of x equals y. That's the definition of a bijection. And it looks rather like the definition of a function. Because the definition of a function is that for every x, there's a unique y in the graph. But to be a bijection, it's for every y and y, there's a unique x. So it has to be a function in the first place, and then you get something that looks like the definition of a function, but the other way around. So this one is for all y in y, there exists a unique x in x with such that f of x equals y. So note that we've carefully swapped the y in y and the x in x around from the definition of a function. Of course, it has to be a function and have this property. So now you've actually got it both ways round if it's to be a bijection. And now the nice thing is bijections do have inverse functions, which we're going to do properly in a minute. And you've seen examples of functions which are and aren't bijections and which do or don't have inverse functions. Let's see what we've got here. As functions from R to R, these functions here are not bijections. It says why not? Well, I'll tell you. X goes to x squared has two problems. It's neither injective nor surjective when you're going from R to R. Okay, so if we're going from R to R, keep track of what our domain and codomain are. So with domain R and codomain R, x squared is neither injective nor surjective. E to the x is injective but not surjective. And x to the x minus x, where every line hit it at least once, that was surjective but not injective. So remember, not injective means there's going to be some horizontal lines hitting it more than once. X squared does that because lots of horizontal lines hit it twice. X cubed minus x has got lines hitting it 3 times, horizontal lines hitting it 3 times even, certainly more than once anyway. So they're not injective. E to the x, the horizontal lines only hit it at most once, so that was fine, but there were some horizontal lines missing it completely. So if we go back and look at those sketches, you should see why they're not bijections, because you'll see that some of them are not injections and some of them are not surjections, and x squared wasn't either. But if you change the codomain, or sometimes change both the domain and the codomain, different things happen. So if you're doing the rule x goes to e to the x, you can map from the whole real line to the strictly positive real numbers, and you get everything once. That asymptote sort of shows you that. If you look at the sketch of e to the x, you do get all positive real numbers exactly once. And you get an inverse function, the natural logarithm, which takes you back again from positive real numbers to all real numbers. And the logarithm function is a bijection as well. If you take the inverse function to a bijection, you get another bijection. Again, x squared failed in 2 different ways to be a bijection, but if you change the domain and the codomain and insist that you're working with the non-negative real numbers, then if you square non-negative real numbers, you get every non-negative real number exactly once, and you've got an inverse function coming back, the non-negative square root. And that is your inverse function. If you start off going from non-negative reals to non-negative reals, then the non-negative square root will bring you back and take you back to where you started. And, but what is an inverse function? Okay? Formally. Actually, there's various different ways of thinking about it, and some of them are quite quick. Okay, so what is an inverse function? I'm going to figure out what an inverse function really is, we're going to look at the identity maps to start with on any set. But here's a reminder that you've done a lot of inverse functions in calculus already, so you should go back to calculus and have a look at all those inverse functions and see whether their notion of inverse function agrees with my notion of inverse function. You see, the functions you deal with in calculus, they might not be quite as strict on what they say the domain and codomain are. So when they claim they've got a genuine inverse function in calculus, to turn it into pure maths language, you need to figure out which domain and codomain you were working with so that this is a genuine bijection so that you can do a proper inverse function in our sense. Okay, now let's try and formalize this a bit. First of all, there's this very useful thing called the identity map that you can define on any set. Even the empty set, though functions on the empty set are not very exciting. There's only one function on the empty set, and it's called the empty function, except that you can vary the codomain if you like. But other than that, there's only really one function on the empty set, and it's not very exciting. So now, let A be a set. The identity map, it's just a map that doesn't move x. You start at x, you finish at x, and that will map you from A to A, and I'm denoting it by id sub A, and it has a very simple formula that id A of x is x. It's obviously a bijection, and it's its own inverse map, in fact. The inverse to id A is id A, which still goes from A to A, and it's certainly a bijection. Okay, now, so what is an inverse function? And it turns out once you've got one, then it's unique. So you start with a function from x to y, and you now take another function coming back again from y to x. So you're going both ways. Now, in this special situation, you're going from x to y and then back again. F goes from x to y, g takes you back from y to x. So that means you can compose either way round. You can look at g of f of x, or you can look at f of g of x, or f of g of y, okay? Now, if g of f of x is x for all x, and f of g of y is y for all y, then we'll say that g is an inverse function for f. It's going to turn out that if you've got an inverse function, it's unique, and it'll turn out that you have an inverse function if and only if you're a bijection. So that's what we're going to be looking at in a minute. But this thing that says g of f of x is x, that's the same as saying the composite function, g composed with f, is the identity map on x. And f of g of y equals y, what that says is that the composite map, f composed with g, is the identity map on y. So we were looking at composites last time. We showed that function composition is associative. That's quite useful, actually, for showing uniqueness of inverses, as we'll see in a minute. If you compose anything with the identity map, you get the same thing again. So if you start with the identity map and you compose something with it that you can, you just get that function again that you compose with the identity map, because the identity map doesn't change anything. And that's true on either side. So if you do identity composed with some function, it's still going to be that same function. If you do some function composed with identity, then that function is still going to stay the same. In fact, it's a bit like multiplying by 1. So if you think of function composition as a bit like multiplication, then these identity maps are like 1, that when you multiply by something, it doesn't change. Okay, so here's the key result then about bijections and inverse maps. So you let x and y be sets, and you take a function from x to y. Now, it may or may not have an inverse function, and it may or may not be a bijection. And in fact, they've got the same answer. The function has an inverse function g, if and only if the function is a bijection, and in which case that inverse function is unique, which allows you, and the inverse function then is a bijection as well. And in view of that theorem, we get that the inverse function could be denoted by f to the minus 1. Now, before I go and prove this, I want to just remind you that we already were using the notation f to the minus 1, even when f isn't a bijection, because we looked at pre-images of sets, and that was defined even if it wasn't a bijection. But we're in luck, because if f is a bijection, and you look at the two different meanings for f to the minus 1 of f, they come out to be the same thing. What are these two meanings? One of them is the pre-image, and the other one is the values taken by the function f to the minus 1 of this set. And normally, if it's not a bijection, only one of those makes sense. When it is a bijection, they both make sense, and fortunately, they're the same. Okay, so if you go back and look at pre-image, you can compare it with this. But let's have a look at how we prove this theorem. Okay, so first of all, I think I'll start by proving that you can't have more than one inverse function using the associativity of composition. Okay? So the proof of the theorem. Let's have a reminder of our setting. We've got a function f from x to y, which may or may not be a bijection, and it may or may not be have an inverse function. Let's suppose that we actually have a g coming back and a g prime coming back. And suppose that they are both inverse functions for f. Suppose that g and, this is uniqueness of inverses, right? Suppose that G and G prime are both inverses for F. What we're going to look at is G composed with F composed with G prime. Which we know is equal to G composed with F composed with G prime. That's by associativity of composition. And let's call this the left-hand side, and this the right-hand side. So we've got left-hand side equals right-hand side. That's just associativity of composition of functions. It just means do the three functions one after the other. And these are both maps from y to y. You can start with y, and you can do G prime, and then F, and then G. And in fact, that's what you do. You do those three functions to get either the left-hand side or the right-hand side. Okay, but because they're both inverse functions, since G and G prime are inverse functions, that's our assumption at the moment, you get F composed with G prime. If you do G prime first and then F, you must get back to where you started on Y, which means you get the identity map on Y. So F composed with G prime is equal to the identity map on Y. That's the same as saying F of G prime of Y equals Y for all Y in Y. But we also have G composed with F. G composed with F means you do F, you start on X, you do F, and then you do G to come back to X. And that doesn't move you, that takes you back to where you started in X. So that's the G composed with F is the identity map on X. Similarly, G composed with F is equal to the identity map on X. So, the left-hand side is G composed with the identity map on Y, which is just G. And the right-hand side is the identity map on X composed with G prime, which is G prime. Conclusion is G equals G prime. That's not the only way to do it. I just wanted you to see an application of composition of functions. So G equals G prime. So you can't have more than one inverse function. I'll just sketch the rest. Okay. Suppose that Y is a bijection. Now suppose F is a bijection. And okay, since F is a function, we'll consider the graph of F. Since F is a function, we have, for all x in X, there exists a unique y in Y with f of x equals y. So that's with xy in the graph. That's true for all functions. But because it's a bijection, it's true the other way around as well. Since f is a bijection, we have all y in y. There's a unique x in x with xy in the graph of f. And now, set S to be the following flip. We do yx in y cross x, such that xy is in the graph of f. Let's give these names here. Let's call that 1, 2. Then the roles of 1 and 2 get swapped. 2 now tells you that S is the graph of a function from y to x. Or 2 tells you that S is the graph of a function and it also helps you to see that it goes from y to x. And 1 tells you that this function is a bijection. Again, it's not the only way to do it. So if you call that function g, it'll be the inverse function for f. I say an inverse function, of course it's unique. This is another way of thinking about the uniqueness. The only way to make an inverse function is to do this to the graph, to flip the graph. This is what you did in calculus when you reflected in the line y equals x to find the graph of the inverse function. Of course, that's only one way round. This is showing that if you're a bijection, you've got an inverse function. So I leave it as an exercise. Prove that if f has an inverse function, then f must be bijective. Okay, so I'll stop there for today.